3 types of shaft couplings. In fact, just give me 2 seconds, I'll shut my door. Yeah, morning. That's a nice classroom. In your bed. That's just chilling. That's a nice relaxed classroom, that one. So who can tell me 3 types of couplings for shafts?
Power and fixed turbine?
No, not the types of shafts. How we join turbine discs to shafts and shafts to other shafts.
Corvic, gimbal, spline.
Yeah. Spline. And
Gimbal.
Gimbal, good, thank you very much. Good, see, we've done something right on Friday. It's Hareen coming out. Okay, good, that was a good start. Which type of engine would probably have a single control on it? Single throttle control. Fixed turbine or a free turbine? So which type of, yeah, maybe have some aircraft have 2 controls, the power and condition lever. Some just have a combined 1 lever. So which one tends to have just 1 lever, the fixed turbine or a free turbine?
Fixed turbine.
What does everybody think? Fixed turbine or free turbine? 1 control or 2 controls?
Two controls.
Ooh, 50-50. Now, normally in a fixed turbine, you have 1 control. Okay, so the power lever we can connected to your propeller control lever, and we tend to find on free turbines we have the power lever and a separate control lever for the classed as a condition lever. Okay, so 2 separate ones. But in direct drive engines tend to just have one lever. So it saves the pilot, saves yourselves from having to worry about putting hands all over the place. You've got the 1 lever, combines everything. Speaking controls, what were the 4 things or the 4 requirements for all control systems?
APRE.
Good.
Accurate, positive, reliable.
Say again, sir?
Effective. Accurate, positive, reliable, and effective.
Good. Thank you very much. Accurate in what?
Accurate in operation.
Yeah. Positive in?
In selection.
Yeah. Reliable?
All conditions of flight.
Yeah. And effective?
Regardless of distance between the flight deck and the engine.
Fantastic. Brilliant. Thank you very much. Good. Right, there's just a few questions. That's everybody just about in, I think, looks at that. Okay. Right, what we'll do, we're just going to move on. Just getting my page right. Move on to turboshaft engines, which is pretty much the same as a turboprop, except a turboshaft. A shaft is usually, or we tend to class turboshaft engines for like the helicopters, hovercraft, and that sort of thing. So we'll have a shaft that comes out, usually to the rear, attached to a gearbox, and then we'll get perpendicular to the gearbox, the shaft going up to a rotor and stuff like that. So we'll look at the 2 groups of these ones. Okay, so let's change my pen. Go. So again, we still have direct drive. Okay, good old fixed turbine, we're all good with that. And we still have free turbines as well. It's just a different terminology for basically a gas turbine engine, either fixed or power turbine, doing a slightly different job. So again, direct drive, just to recap, remember direct drive is the spool is mechanically coupled to the engine. So free turbine, example there, twin spool, it isn't, it's just a shaft, a turbine and a propeller, just as we've seen already. So free turbines are safe for, especially for a helicopter, or that sort of thing. We can have normal standard gas turbine engine, but this time instead of the shaft going forward, we might have the shaft going rearwards, and that'll be connecting to a gearbox. So you can see the turbine here, but again, isn't connected to the engine. It's purely the gas coming out of the combustion chamber through the turbine of the first spool, and then hitting the next turbine, connected to a shaft, and then that shaft will be fitted to some sort of gearbox, or potentially, if it was a turboprop, a propeller. But we're looking at turbo shafts. Drive system. Well, if we look at the side here, we have got a twin engine, basically like a twin engine helicopter. Okay, so we've got engine 1 on the right hand side, and then, engine 1 left hand side, engine 2 on the right hand side. So you've got your standard engine. There's your free turbine. There it moves along to a takeoff, like a PTO, like one of the joins we saw before, a power takeoff, which would be the same as a gimbal. Then we'll have a big gearbox here, okay, and this gearbox will be attached to a rotor on a helicopter. And we've got 2 engines, 2 shafts, all rotating the same gearbox. What could you see can potentially happen here? Could go wrong. We've got 1 gearbox, but we've got 2 engines spinning the same gearbox.
Main gearbox.
What potentially could happen or go wrong?
Direction of rotation.
Yeah, direction of rotation. Yeah, but it's this. What's called the main gearbox is called what's called the free wheel unit. If you think of some cars, going back to my cars again, here we started already in the first few minutes of speaking about cars. Any rear wheel drive car or a big HGV has got a rear wheel drive. It's got a differential, and some of you might know a bit about differentials. A free wheel drive gearbox works on a very, very similar principle. Although you have 2 engines running the same gearbox, there's a potential that if one engine breaks, you're lucky it's a free turbine, it won't affect the good engine. And we're going to speak about how this works, okay? So we're going to look at what's called a free turbine setup with a free wheel unit. Its name pretty much says what it's designed to do. It's a free wheel setup. Oh, personality coming in again. Okay. So basically, we've got your gearbox. So your inputs, so there's your power takeoff here and your power takeoff there, represented here. So you've got the power takeoff shaft and the other power takeoff shaft from both engines, hitting a reduction gearbox in this freewheel unit assembly. Again, so we're now changing the angle of direction of rotation. So we get up the way, in this case for a helicopter, for a rotor, and along the back to a tail rotor, because helicopters need a tail rotor to stop the helicopter spinning around. Okay, we'll come on to that in a bit. So the freewheel unit allows 2 engines to rotate the same component. It allows it to change direction of power, to going up the way and a long way. And through the various reduction gearboxes, we don't want the big rotor on the top spinning as fast as a normal engine, because it would just be too fast. And likewise for the tail rotor, although the tail rotor is slightly smaller, it also has a reduction to spin at a certain speed. Again, that's all calibrated by the designers. All right. Let's get a bit up there. Now, because of the size of the rotor and the size of the tail rotor, again, there has to be a fail-safe sort of problem in there. So there's lots of things we look at. We don't want to say, let's say we have a broken engine. We certainly don't want the broken engine to stop the good engine from running. And there's a few fail-safes we shall look at. Okay, and make sure that should there be an occasion like that, it doesn't affect it. So the gearboxes are arranged in such a way that, yes, both engines can spin the gearbox one way, but if one fails, the other one can still spin the gearbox, but it won't affect the broken engine, and the broken engine certainly won't affect the gearbox. So a very clever bit of gearing within there. Again, back in the hangar, we've got a nice freewheel unit. We usually take students out to show you, but just be aware it won't affect a good engine should one engine break down. We'll come on to that in a little bit. Okay, who's that coming in? Push back. Okay, just bear with me. All right. So we mentioned about gearing. Again, we looked at reduction gear module 17. Again, we'll just do a bit sort of small recap on this one as well. I'll show you some of the bits and pieces. Again, as mentioned, we don't need, well, we can't have the blades spinning as fast as the main engine here. So we have various types of gearings in a reduction gearbox of whatever variety. Now the main rotor could be as low as 250 RPM or maybe 530 revs per minute, where the main engine can be spinning anywhere from 10, 20,000 RPM. Okay, so you might have a reduction gearing of maybe 100 to 1 or 5 to 1 for the tail rotor and that sort of thing. But again, most of them are typical sort of spur gears. The ones in the main gearbox for the freewheel turbine will probably be epicyclic gears or bevel epicyclic gears, and bevel ones as well, even some helical gears in there. The main types of reduction gear we'll look at, again, just a bit of recap from what we've done already in Mod 17. Spur gear, epicyclic, and bevel epicyclic. Spur gear, again, straight cut gears. Again, so just to recap, there's your crankshaft and there's your driven gear. So again, the crankshaft gear, the driving gear is usually the smaller one, because if that was bigger than the driven gear, then the driven gear would go a lot faster. Okay, so we'll go through examples again. Typically used on inline engines, epicyclic. Again, what we've got the sun gear in the middle. We've got the planet gears all spinning independently around an arm. Okay, and then we'll have an annulus or ring gear, excuse me, which will either be stationary or will move. It depends on the construction. Here, 3 planet gears, an annulus ring gear. And where high torque is to be transmitted, the gear tooth used is what's called a double helicule or stew gear. Bevel epicyclic, again, just to recap again from 17. So remember, the crankshaft gear on this side, that'll be from your main engine. Then we'll have the planet gear, a bevel one, which will, as it's spinning round, circular like that, it's also going round the actual casing, because this fixed gear, as it sounds, it's fixed, it doesn't stay. So it's the fact that this axis here is actually rotating around the engine, but as it's rotating, it's also rotating that way as well. Okay, so it's going 2 movements. The actual gear itself spinning, but it's also spinning on a shaft. And this shaft here is connected to a propeller shaft. So as that is spinning round and round and round, that's also spinning your propeller or rotor, depending what it is. Okay, so that's your bevel epicyclic. To oppose bevel gears of different diameters. Okay, so just to recap, larger is your driven with a crankshaft, and smaller at the front, again held stationary. So again, this is just a slight recap from within 17. And your planet pinion gears are free to rotate. So again, that was just the side-on version of it. So again, there's your crankshaft from the engine. There's a bevel pinion gear, which is attached to the shaft for the rotor or propeller or gearbox, whichever it is. Again, this is typical of a propeller one. Again, there's your fixed stationary gear. So this one, as I say, is spinning round and round on a pinion there, but it's also spinning round due to the crankshaft. All right. Again, the gearing all designed to be proportional to the speed required for that type of rotor. And typical formulas for spur gear is gear ratio is a driven over drive. Example we showed you before, just to refresh yourself, if the drive gear has 24 teeth, which is a smaller gear, and your driven gear has 36 teeth, well, that's a ratio of 1.5 to 1. In other words, the drive gear has got to spin 1.5 times to rotate the driven gear once. Again, these aren't in your books, guys, these are just examples got. Do have this one though, again, just shows you the internal, external. So the driven gear, the bigger one, 100 teeth, the drive gear, which is the crankshaft, 50 teeth. So it's simply 100 over 50, which gives you a ratio of 2 to 1. In other words, this has to rotate twice for this one to rotate once. And if you put the same gear inside, okay, it's still 100 teeth over 50, still a ratio of 2 to 1. Just showing you a slight different way of doing reduction gears. Epicyclic one, again, driven over drive. However, we can have it drive gear plus fixed gear over drive gear because of the annulus. So we add up the teeth of the drive and the fixed over drive because of the annulus on the outside. Your drive gear and your fixed gear is just your planet carrier. That's what the class that is. Typical gear ratio, drive and fixed over drive. So example we've got there is 50 teeth. Ring gear is 100. So the drive and the fixed is 50 plus 100 over 50. It's 150 over 50. Divide that, gives us 3. So it gives us a gear ratio of 3 to 1. Okay, this time we've got a sun gear. It's got 50 teeth, and the ring gear has got 100. But it's the same formula, so it's drive plus fixed. Still 100 plus 50 is 150 divided by 100 this time, gives us a reduction gear ratio of 1.5 to 1. That's represented here. So the drive gear and the fixed gear is 100. Okay, there's your 100 there, and your 50 for the sun gear. All over the drive gear gives you 1.5 or 3 to 2 ratio. And it all depends. You can write this that way, or you can flip upside down, depending if the annulus, or the ring gear here, is stationary or rotating. You'll just get a different ratio reading. It's just an inverse version, that's all. Okay. So again, as I said, can also be written as driving gear plus fixed gear, which is in your books. Okay. They won't give you the same driving gear plus driving gear fixed gear or driving gear plus fixed gear. They both mean the same thing because some gears are stepped up, some gears are stepped down. Okay. But the whole purpose is it is a reduction gearing. And just for a good old recap, okay, get this to work again. If I can get to work, try to get to work. There we go. Okay, just to show you again the relationship of all the gearing. So a typical spur gear is your crankshaft, reduction gear, and then internal, and then we add the planet gears around the sun gear, so it's moving the annulus. And then we can actually make the annulus stationary, and then move the actual planet gears themselves, which would be attached to a propeller, which is pretty much normal. Okay, and in starter motors as well. So just a few different versions of the same thing. Okay. But again, this is what you would cover first before we do module 17, but we did module 17 first, so we've seen this already. So hopefully just a bit of a recap. All right. Righty-ho. But in your books, as I say, the formula, just remember it's driving gear over driving gear plus fixed gear. But again, as I say, it just depends if this part's moving or rotating. It still means the same thing. Right, let's move on to turboshaft controls. So with the control system, we're going to look at what's called an anticipator. Now, we have to look at helicopter controls because they've got gas turbine engines, and you might end up working on helicopters potentially. You might fancy a changeover from fixed wing to rotary wing. Okay, so we need to understand two levers or basic levers that are within the helicopter system, and these are the cyclic pitch lever. This lever is, think of it as the joystick. You've all played Xbox or PlayStation or something like that, you've got sort of joystick. Well, that's the one that makes you go forward, backwards, left and right. Okay, that's a cyclic. Now, the main thing to remember the cyclic one is it controls the rotor blades independently of each other to produce motion of the vertical axis of the aircraft. In other words, it will only move one blade, change the pitch of one blade to either move it backwards, forwards, left or right. So it's independent, only one blade at a time. So that's just cyclic. Think of cycling as going round as your joystick. Okay. Other one is the collective. Well, if it's collective, it's collecting. It collects them all. That changes the pitch of all the rotor blades together. So a cyclic pitch is the one in front of you. The collective one is one to your usually left-hand side, depending on the aircraft type, and that's the one that makes you go up and down. Okay. In other words, it will change the angle of attack of all the blades to increase the angle of attack to increase lift, which will help lift the helicopter up. And likewise, it also does the throttle. Older days, the collective lever would also have an independent throttle, like a twist throttle like a motorbike. So it was up to the pilot to ensure they had the correct amount of power from the engine. Nowadays, the collective, you just bring the lever up and it automatically does the throttle for you. So it takes a bit of load off the pilot. Okay. We're going to look at a thing called an anticipator, which helps take the responsibility out of the pilot's hands, so it gives them less to worry about. All right. So the anticipator itself, well, if you imagine you've got the rotor spinning round and round, basically a set of wings that are spinning round and round. If you change or increase the angle of attack, well, you're going to get more lift, which is great because you want more lift to lift the helicopter up. But unfortunately, if you get more lift, those big flexible rotors are going to bend like a banana. Okay, so as they bend, let's change that again. As they bend, you actually lose a bit of wing surface. All right, so say that when the rotors are stationary, you will get a distance from one rotor tip to one rotor tip of so much, about that much. Okay. As the wings bend, well, that distance decreases because the blades have bent up the way. So I can see here, you've actually, the distance has decreased. So if you decrease the length of effectively a blade or a wing, well, you're going to decrease lift. So the rotors are getting lift, but because they've decreased the amount of surface area, then you actually, the helicopter loses lift. All right, so what will happen is the helicopter will start to come down. Now an anticipator will, and as it sounds, anticipate this, and it will actually speed up the engine by putting more fuel to the FCU to speed it up. And through centrifugal force, the blades that were bending like that will now be thrown back out to centrifugal force to a straighter angle, still maintaining the angle of attack to increase lift. So basically, it keeps the helicopter up. All right. So anticipator, as soon as you select to go up, it thinks, oh, wait a minute, we're going up. We need to spin the engine faster to make sure the blades stay down. Even though they've increased their angle of attack, they need to keep the same distance from tip to tip. Otherwise, you'll get a sort of cone effect going on like this, as it shows you here. Okay. So basically, what we're doing is compensating for the loss, going there, of disc area, because a rotor spins making a disc as such, just like a propeller. As a propeller, remember in module 17, we get the bending force of the propeller trying to go forward. So in effect, you're decreasing the amount of propeller disc area. All right. So this is what the anticipator does. By centrifugal force, by making the engine go faster, it throws the blades out more force, which keeps them down, which keeps the helicopter up. So should no anticipator be fitted, the collective pitch, when raised, will create a drop in RPM, because if we're getting the stress of the rotors trying to get more lift, but that's going to slow the engine down. Exactly the same as we saw in module 17, we increase the angle of attack on the propeller, that slows the engine down. Well, a helicopter is just the same, except the rotor is above it instead of in front of it. So if we increase the angle of attack, yes, we increase the surface area of the blade, or the rotor in this case, which is going to put more stress on the engine, which will slow it down. Well, if it slows the engine down and we've decreased the size of the disc, then the helicopter is going to come down. So we need to have an increase in RPM. So that drop in RPM is known as static droop. Make a note of that one, okay? So no anticipator fitted, you'll increase your pitch of your rotor, which is great, but that will also slow down the RPM of the engine. Okay, who's that? Okay. Does that make sense so far, guys? Yeah, it's just like a propeller helicopter, a propeller aircraft. We've got the bending force going forward, so it slows the engine down. Well, a rotor and a helicopter, same thing, except instead of being in the front of the nose, we've got it going up the way. But the angle of attack is increasing. It's trying to pull the helicopter up, but it's putting more stress on the engine because we've got a greater angle of attack. So there's more air it's trying to push around. So it's going to slow the engine down, which overall, yes, we get lift in the blades, but we don't get lift on the helicopter. So we need to increase power. And as I said before, in the older style helicopters, it was up to the pilot to physically twist a throttle attached to the collective. So there are two main types of anticipator system. Just like we saw with torque systems, we've got mechanical and electrical. Okay. All right, so basic anticipator, again, this is the basic electronic diagram. We'll just quickly go through. You don't have to remember the whole thing here. We're not going to do all the formulas and all that good stuff. But what you can see here, here's your collective lever in the cockpit. So plus or minus, it wants to go up or down. So by changing a variable reference, a signal into the system, an electronic signal, it will give a preset. There'll be a fixed reference signal from your NF. What would NF stand for? What would NF?
Free turbine.
Free turbine speed, yeah. So we've got, if you look over here, we've got a sensor attached to your free turbine, which will be attached to your gearbox, and the gearbox will be attached to your rotor. So we're sensing the speed of the free turbine. Okay, the engine's just doing its own thing. Remember, free turbine, not mechanically coupled. So if we want to go up, we increase the angle of attack of the rotor. Great. The blades start to increase lift, but because of the extra air they're pushing, they're going to slow the engine down. So the RPM signal here will give a signal to the system and say, I'm slowing down. But wait a minute, you've asked for more lift. Ah, right. So nice little calculation there. The engine electronic unit will say, okay, the pilot wants to go up, but our turbine has slowed down. We need more fuel. It will anticipate this as soon as he moves that stick, all before the actual helicopter drops. So it will provide more fuel to the fuel control unit, which then spray more fuel to the burners, more fuel, more oomph. The helicopter will rise in proportion to what the pilot wants. Okay, so this is what all this electronics does. It's just sensing the speed, and it will maintain the speed of the LP turbine depending what the pilot is doing. And likewise, if the pilot wants to go down, he's going to decrease the pitch. Well, like in module 17, if you decrease angle of attack on propeller, it's going to speed up. So we don't need all that fuel. So if he's decreasing the angle of attack, then again, unless we change the input to the fuel pump, then there's a chance that the free turbine will overspin, which will overspin the gearbox and so on. The rotor will go too fast. So again, by going down the way, the potentiometer here will give a signal, check what the speed in the LP turbine is doing, the free turbine, sorry, and decrease the fuel output to match, and that'll stabilize. Okay. So again, it's, as it says, it's anticipating the action of the pilot's input on his collective stick. Okay. And also with the free turbine sensor. Okay, so that's pretty much you need to know about the basic setup on that one. That's electronic. Now we've got the over turbine speed one. So in the event of a failure, let's say the free turbine shaft breaks, what's going to happen now? What's going to happen to the free turbine speed? Will it go up or will it go down? If the gearbox snaps in two, what's going to happen to the free turbine speed?
Goes up.
Yeah, it's going to go faster because it's not spinning the gearbox, so it's freer than a free thing. It's really free now. So remember, the gas in the engine is going to spin that turbine, which now is not connected to anything. That's going to get really, really, really fast, which is not a good thing to happen, is it? So just in case that happens, the overspeed point will feel catastrophically for some reason. The pilot will have almost no time to react to that. So we need an automatic type system to help that pilot. He's got to worry about, I've just lost an engine, okay, or power to the gearbox. If he's got two engines, that's not so bad. If he's lost his one engine, well, he's in a lot of trouble. But if in a twin engine helicopter, he's going to get the warning, oops, he's going to see his speed sensor will indicate overspeed, and so he has no time to react, so he needs something to help him work that out. So there again, there's the gearbox snapped. Oh my goodness, that's not good. The sensor will give, again, to the actual unit, it will say we've got now overspeed condition. So this example, the fuel solenoid will close and prevent fuel flow should that turbine, the feed turbine, get a speed of it reaches 120%. Okay, so 120%, well, that's 20% too much. So it's going too fast. So what it'll do, it will shut down the engine. There's no point in the engine running trying to spin a broken turbine. All right. And we've got a thing what's called 25% relay, will cause a warning light to illuminate in the cockpit in a steady state until the RPM reaches 25% when it will extinguish. Once the system is shut down, so all the system here will shut the engine down. It will also inhibit the good engine from shutting down because we need that engine working. And if he's really unlucky and loses another shaft, well, that's it. He's pretty much in a lot of trouble. But it will shut the bad engine down. We don't need the engine spinning, but it will also prevent the other engine from automatically shutting down. So it gives the pilot the best chance to recover that helicopter as best as possible. Okay. There we go. Example, the fuel solenoid will close and prevent fuel flow to burners when the feed turbine reaches 120%. And as I said there, the 25 relay will cause a warning light to illuminate in a steady state until it reaches the RPM 25% when it will extinguish. So once it slows down, it will then go out because the pilot he needs to know the engine shut down. He doesn't need to know what's happening. As long as it's slowing down, that's fine. He can concentrate on what's happening with the rest of the aircraft. Once the system is shut down, as I said before, the affected engine will inhibit restarting. In other words, it won't allow the pilot to restart the broken engine. Well, what's the point? There's no point in starting a broken engine. But it will also, the main thing there is inhibit the automatic shutting down of the good engine. All right. In order to restart it, it will be necessary to push the resetting button 1 to put all the circuits back to the default position. But because it's slowing down to 25%, now you could argue that you might need some electrical power or hydraulic power, but off the engine, probably not. You're probably just going to leave that engine shut down because you've got a broken gearbox. Well, there's no point in trying to start, well, broken shaft, I should say. Okay, that's basically it for anticipators. Anticipator does what it says on the tin. It anticipates the action of the pilot if he wants to go up or down. In other words, it supplies more fuel to the fuel control unit to make sure we don't get static droop. Okay, so it maintains the level or the disk area of the rotors at the correct time. But should something happen to the LP free turbine, then we've got a system in place where it will automatically shut it down if it reaches 120% and inhibit the bad engine, but also inhibit the good engine. Okay, so we don't have bad engines trying to work in. Your two main levers, your collective and your cyclic. The cyclic only operates one propeller blade or rotor blade at a time. With collective, well, just think of collective collects everything, so that adjusts the angle of attack for all the rotor blades. In other words, collective does your up and down, your cyclic is your joystick in between you, and that does your forward, back, left, or right. Okay, that's we just think of cyclic as going round, so forward, back, left, and right, and collective up and down. That is it. Okay. Olden days, throttle was attached to that, twist throttle. Nowadays, new one, it's all automatic, and the anticipator takes care of that. Okay. Right, let's just double check on there. Any questions on that? The reduction gearing we've covered already. Got a quick run through there anyway. Might want to make a note in your books. I think it's the same in your old books anyway. Reduction gearing, as I said before, about 100 to 1 for the rotor and about 5 to 1 for tail rotor. Again, they're just examples. Yeah, it's okay for that one. Drive systems, we'll have a fail-safe. Yeah, we've got that sorted out. They're just examples. Turboshaft, very similar to turboprops. There's not much difference except you've got a shaft coming at the back of the engine, going to a mere gearbox, which will have a freewheel unit attached to your rotor and attached to your tail rotor. And again, depending on the setup, will give you the correct gear ratio. Okay. Anything else I want to go through there before I move on? Remember the static droop. As I said, when the blades they move up, that decreases the size of the disc area, so it can put more strain on the engine, which means you're dropping RPM, So in theory, unless you put more power to the engine, the actual helicopter is going to go down. Although you've selected up, you're actually putting more strain in the engine, which will slow it down and actually lose height. So hence why we need to speed the engine up, centrifugal force, throw the rotor blades back out to keep that disc area, and that will allow the helicopter to rise according to the selection. Okay, anything else? Annotations we've just gone through there. NF, free turbine. Okay, and that is pretty much it before we move on to APUs. Any questions there, guys, for that part? Nice little section. Hopefully not too bad. All good. All good. Right. Good one we've got coming up is APUs. Well, we'll start on APUs and we'll go into the start sequence and bits and pieces, and we'll recap that. We'll do a little bit now, and then we'll go for a break, and then we'll recap that when we come back, because it's quite a lot with the APU side of things. Okay, so let me reset this slide. Okay, it's all now. Right. There we go. Getting back to there. Bang. Okay. All quiet so far. So everybody must be happy. Right, we're finally getting on to APUs, auxiliary power units. A nice little diagram we've got there, a cutaway. Based on APU, it's just a small jet engine. That's all it is. And you can see from there, we've got a compressor at the front. What type of compressor is it?
Centrifugal.
Yeah, centrifugal. We'll have some turbines as well. And then we'll have one shaft, and then we'll have some nice reduction gearboxes going on. And then we'll have a power output to wherever. Now, some of these ones will connect to a gearbox. Some are purely a jet engine attached to a smaller gearbox to hydraulic pumps, generators, that sort of thing. We'll have air supplies. And it's basically its own little jet engine system. What's the purpose of an APU, though?
Power and pressurized air.
That's it. It's a power unit. Electrical power, hydraulic power, up to a certain amount. Some APUs we can't do everything at once. We can maybe use one hydraulic system and then switch over to another one. We can't also do everything, or we can use it for everything, but very slowly. So we can use it for checking controls on certain aircraft controls, as long as you operate them slowly. But certainly electrical power. So every time you go to a big aircraft, you go on a holiday or wherever, you're going flying to another country, you'll hear the APU running. Again, a lot of people think it's a big engine. It's obviously not the big engine running. It's just the APU providing electrical power initially. And normally these APUs will switch off just after takeoff, just in case an engine failure, we still electrical backup. But pretty much it is what it is. It's just a very small gas turbine engine, which you can leave running for as long as you want, pretty much, taking a tap of fuel from the aircraft. Okay. But again, the maintenance also happens to be very similar to a standard jet engine. Tend to find them near the tail, somewhere out the way, especially in the bigger aircraft, because they look like a small engine. They're very noisy, very whiny. Okay, so we tend to keep them at the back end, out of the way. All right, makes it a bit more awkward. The bigger the aircraft, the higher it is out of the way. Okay. We need some sort of air supply. Just like a normal jet engine, we need air supply coming in, and you will have certain doors. So we've got a little APU door here. Okay, so you can see facing in, and there's a little intake in there as well. Sometimes it could be a panel that just comes out the side. On my old aircraft, it was just a door that came out. That was actually underneath the tailplane about here on the small Tornado aircraft. And as we'll find as we go through the starting cycle of one, if that door doesn't open, then it won't allow the engine to start. It's a safety thing, because if the door doesn't open, we have no air supply. Well, there's no air supply, then there's no point starting the engine. Okay, so it can be through a single, twin intakes. All depends on the type. These are actuated by probably electrical actuators and ramrods. Again, and you'll get an indicator in the cockpit saying this is working as well. So basic APU supply, compressor discharges air not required into what's called a inlet plenum, a plenum chamber, like we saw last week. As you see, output shaft in the back, you've got a turbine, and depending on the type of APU, this time, in this one example, we've got a double impeller, double centrifugal impeller, which is drawing air in from compressor section here. Okay, into another compressor, in this case, just a different type. Reverse flow combustion system, purely for space. Okay, so the combustion can is in line, just up the way, but this is the type it is. Okay, it's just for this specific diagram. Again, you have igniter, turbine section, and your exhaust section as well. And we'll have some bleed air, which we can bleed off to use for whatever. Okay, so it's all through it. So there's the inlet plenum chamber. It says it just helps stabilize air, not required for start. Excess air we don't need. Automatically regulated and will provide the correct amount of air without overloading the APU. Fuel, yeah, it needs fuel. Fuel supply from one of the tanks in the main fuel system from or via a solenoid operated valve. The aircraft I worked on, it was #1 tank. Again, it all depends on the size of aircraft, where the supply of fuel from. If you've got an APU way at the back of the aircraft, there's no point in taking fuel from the very front tank. So depending on the aircraft, they will take some fuel from a tapping from one of the tanks appropriately. Regulated by a fuel control unit, which controls acceleration of the APU. Now, APUs have pretty much one acceleration, start and fast. Okay, if you ever go on YouTube, there was an individual took a small APU and he fitted it to a go-kart. Thought it'd be quite funny to fit to a go-kart. Didn't realise there was no throttle on it. So when you start it up, it's got an automatic clutch. So as soon as you started it up, it went up to 100%, and his go-kart went down this little runway faster than the fast thing. And he eventually managed to stop it without killing himself, and they eventually fitted a regulator. So yeah, don't go fitting an APU to a little go-kart going down the streets. It's one position only. So yeah, regulated by a fuel control unit, controls acceleration and maintains speed by proportioning fuel flow to load conditions. When load conditions mean when we're tapping air off for air conditioning, cabin conditioning, or we're maybe using hydraulics. So you put hydraulics on, you strain the gearbox, which means the APU has to maintain that speed of the gearbox as well. Lubrication, it's got its own self-contained system. So it will have its own oil tank, it'll have a pump, a filter, cooler, and again, oil jet lubricates all the gears and the bearings within inside that APU. And we have a monitoring system of operation, again done by indicator lights and instruments associated with functions such as oil pressure, temperature, and quantity as well. Okay, so you can have this as an engineer's panel beside the APU or compartment SPS bay, and you also might have this in the cockpit as well. So again, it's just a small jet engine doing its own thing. So starting ignition, like any other engine, we need rotation. So rotation engine for starting is by an electrical starter, like your cars and small motorbikes. Again, connected to a drive shaft in the accessories gearbox. And power for the starter, again, can be obtained from the aircraft batteries or also from an external source. And strange enough, ignition system is the high energy type and controlled, from the master control switch. So again, high energy, that means dangerous. So remember the rules. Your spark plug igniter is going to be usually the air gap type. So if it's an air gap type igniter and you're going to work on it, what are you going to do first?
Move low tension.
What are you going to do first? If you're going to change igniter and APU, what do you think you're going to do first? And it's an air gap igniter.
We have to trip the CB first.
Yeah, CB's first, yeah. And then?
Then we have to remove a low tension.
Yeah, low tension, yeah, to the power source, the HIU, yeah.
Then we have to look for what type of spark plug we are using. Then we have to wait for 1 minute or 3 minutes.
Yeah. Well, usually in APUs, you'll probably find they are air gap type igniters. Very rarely you get surface gap ones, although some of the modern ones, they could potentially be doing that. But normally it's air gap ones. So you're looking at 3 minutes. Yeah. But good. Good, that's the correct order. Keep safe. Or as I said, do end up doing the funky chicken dance once only. Right, cooling. Yeah, we need to keep this thing cool. Smart jet engine. So it needs to be kept cool as it's running, because it could be running for long periods on the ground, and especially if you're in a hot country, hot environment, that could overheat. So we need to be able to keep it cool. So cooling ventilation of the APU compartment normally provided by a fan, so actually its own separate fan, again driven by an accessory gearbox. Air is also brought in from the fan for cooling the AC generator and also APU lubricating oil. Anti-icing, well, it's inside, but it's potential. It could be an extreme country where it's very cold, so again we need to protect from anti-ice environment. So some APUs, the air intake is protected against ice formation, again by using hot air or bleeding air or hot air from a compressor over the intake socket, just like we saw on your standard jet engine. Fire detection, yeah, it has its own little fire detection system as well. So detection and extinguishing of a fire in the APU compartment is normally accomplished by a continuous wire detection system, like the ones we spoke about last week. It has its own single shot fire extinguisher, because there's no point in having an extinguisher for an APU from the engine one, because APUs tend to be used only on the ground. Very, very occasionally they might use an APU in the air. There was an occasion where there was a slight fault, and for some reason the pilot kept the APU running, and unfortunately for him, a few events happening, one of the mounting bolts had failed and they actually lost the aircraft, but it wasn't his fault, it was just one of those things. So yeah, no point in using a fire extinguisher on the ground, because you know, safety people there, and also it's on the ground. There's no point using an engine fire extinguisher. And remember, like we saw before, we'll have indicator discs for discharge and pressure relief, depending on the type of system we've got. You can just see the type there. Is the APU engine shroud, its own little fire bottle with all the usual bits and pieces that go with the fire extinguishers. Lubrication system, yeah, components are mounted on an APU and consist of roughly an oil tank of 1.5 US gallon capacity. Again, you can do conversion of that, I'm sure. With an oil filter, just like a normal engine, and a dipstick, or it could be a sight. It could be what do you call it? Fiber optic. We shine a torch in, which is the sort of one we had on our Tornadoes. The tank will contain a level switch, so if it feels a level switch, that'll be connected to a warning, and probably won't let the APU start as well. Which operates within 1/2 quarts of the oil remaining in the tank. So we're looking at an American system here. But again, you would be making sure, depending on the aircraft you're working on, how much oil should be in there. Oh, a pump, yeah, just like a normal system. You need a pump consisting of a pressure and scavenge sections, again driven by a common shaft from gearbox, just the same as a standard jet engine. You'll have a pressure relief valve that opens at 90 psi, PSIG, just PSI gravity, it's the same thing. System pressure allows oil to bypass to inlet side of the pump, and that maintains nearly constant pressure all through the system. And the APU is by positive pressure, dry sump system. In other words, dry sump's got external oil tank, which cools and lubricates gears and the usual bearings as well. And as we've seen before with the standard jet engine, we also have a filter with a bypass valve. Remember, filter keep the oil system clean. Bypass valve, should the filter become blocked, it'd be better having some oil than no oil, and likewise if it's a very cold condition as well. And also the system components are mounted on the APU, and you also have a oil temperature switch. And we mentioned about the oil temperature of 124 degrees, which oxidizes. So again, we want to see that. It will have a low oil pressure switch, which we call number 1, or shorthand to LOP1. We'll go into this a minute more. We'll speak of this after break time. So low oil pressure number 1. It closes at 4 psi, and when closed, the switch allows ignition and fuel to the combustion chamber. If it doesn't close at 4 psi, it means we have no pressure in the system. So what it means by that is when we start to turn the APU, if there's no pressure build up because maybe the pump's failed, then 4 psi, that's nothing. That's like the same in your cars. When you put your car ignition on, you'll see a battery light, you'll see an oil light, And as you turn the engine, the oil light goes off pretty much straight away. That's about the same again, 4 or 5 psi. Well, if this switch doesn't go off, well, there's no point in starting the engine, or the APU in this case, because we've no oil pressure. If you start an APU without oil pressure, it's going to seize. So one of the first jobs is number 1, or LOP1 switch, low oil pressure numbers 1. Make a note of those numbers. Then we'll have number 2 switch, or LOP2, another low oil pressure switch. Now this one opens at 45, or is armed at 45 psi. So when the oil pressure is building up, it will trigger this switch to arm itself, and it will stay armed, and it will sense the oil pressure in the system. And if that oil pressure drops to 45 psi, it will then switch or shut down the APU, because we're losing oil pressure. We might have a leak or a fracture somewhere, the pump seized or whatever it is. So if it senses the oil pressure dropping to 45 or below, it will automatically shut down that APU, and that will protect the APU from any further damage. So all the oil system, you need a cooler, oil cooled by air prior to return to the tank, yeah, so we need to keep it all the same. And there's a basic APU oil system. So again, just like a jet engine, up at the top here, we've got a tank. We've got a filler and maybe dipstick or dropstick or side glass, whichever version you've got. Baffles to stop the oil sloshing back and forward, okay. You have a turbine bearing cavity vent, so an air no oil valve, so allow air in and air out, depending expansion and contraction. We'll go to a standard pressure pump. Again, it'll be a spur gear type pump with its own pressure relief valve, just like we saw with the previous systems. Again, it'll have its own high pressure filter. And then we'll go through to your oil temp switch, which senses it gets 124 degrees. Then we'll have your 2 low oil pressure switches, number 1 and number 2. So remember, number 1 activates at 4 psi. If it senses 4 psi, it will allow the ignition fuel to continue. If it doesn't, it will shut the APU down. Low oil pressure switch, remember, it activates at 55 psi, and if that pressure drops at 45 psi, it will also automatically cut down or shut down the APU. Then if everyone's happy, that's great. The oil will then go to your rear bearings, your front bearings, and any other accessories involved. And then again, we've got a scavenge pump. Okay, now we've got more gears there to draw the oil back to the tank, and again via your oil cooler. Okay, and depending on the system, you will also have, it doesn't show in this one, there will also be a magnetic chip, probably somewhere in the scavenge line, just probably before the pump, to be honest. And there might be a strain, depends, but there's always a chip, because you want to detect what's going on. Okay, there's your oil level switch, forgot to mention. So if that gets too low, that'll give a warning in the cockpit as well. Okay, so a very basic system, very similar to what we've seen already, not much different. So hopefully that makes sense now compared to what we're looking at. Again, with the dash line, that just represents that this scavenge pump and this pressure pump, the filter, the relief valve are all within a set component. Okay, not a very big component at all. Pretty basic, but it's all it needs to be, just a basic jet engine. Okay. Right, folks, let's go for our first break of the day. We'll come back and we'll do a bit of recap, and then before moving on. Okay, and we'll. Okay. Right, so that was the oil system. Any questions on the oil system or any parts we've covered so far? Everybody happy? All good? It's all quiet. Hopefully everybody's awake. Everybody got to sleep yet?
We have 2 low pressure switches, right?
Yeah, 2 low pressure switches, yeah.
So one is to allow ignition and fuel flow.
Yeah, that's the first one, yeah. Opens at 4 psi. If it senses pressure at 4 psi, it will allow...
And the second one?
Yeah, second one, when the pressure builds up, provided the first one senses 4 psi, it will allow the ignition fuel to continue, yeah? So as the engine starts to speed up, the oil pressure will build up because the APU is going faster, which means the oil pump's going faster, more flow, more pressure. So LP2, once the pressure reaches 55 psi, it will activate or switch on LP2, and it will sense the pressure, and provided the pressure stays above 45 psi, it's fine. But if the oil pressure goes below 45 psi, maybe a leak or some fault, that will switch the APU off. Okay, so it's sensing the pressure. Anything above 45 is fine. It will only activate once it reaches 55, but once it's activated, it will stay on, sensing the pressure, and if the pressure drops to 45, it will switch it off, switch the APU off. Okay.
Okay.
Right. So LOP1 and LOP2. We'll see how it all interacts in a little minute. I've got a nice little starting sequence coming up shortly. Any other questions?
No.
Okay, good stuff. Right, we'll move on to the fuel system now. So again, just very similar to everything else. Fuel system, again, fuel control system is going to have a fuel pump. Acceleration control will have a governor. Okay, there's no in between, there's no slow, medium and fast. It's just, it will start, be controlled, and it'll go up to maximum. Okay, so there's no in between as such. And the governor will control overfueling, etc. as well. And you'll have filters, just like a normal engine. And you also have a high pressure relief valve and solenoid valve as well. Okay. Change that there. All right. Generally, the fuel supply, again, to the APU combustion chamber is automatically scheduled during acceleration and constant speed during the fuel control unit. And these components are located in the APU accessory section. So there's a basic schematic, just like the oil system. All right, again, well, one of the main fuel tanks in the aircraft will supply the fuel through an APU fuel shut-off valve, which opens when you master switch. When you switch the master switch in the cockpit to on, that will allow fuel to go to the APU. That will go through an LP filter, a basic filter, and then once the engine starts to rotate, round about sort of 10%, that sort of thing, the fuel solenoid valve opens and the fuel is supplied to combustion chamber. Well, 10%, then it must have, going back to the oil system must be more than 4 psi, because remember, the LP1 switch will switch off, won't allow ignition or fuel to go to the burner unless your oil system gets to 4 psi. So at 10%, your oil system has pretty much got enough pressure to actually start the sequence. Okay. Now the quantity of fuel supplied, again, is scheduled by the acceleration control and a bypass valve, senses pressure, etc. Okay, so what have we got? So you've got an APU fuel shut-off valve. There's your fuel tank, again, from one of the fuel tanks on the aircraft. It's not a separate fuel tank, it is one of the fuel tanks on the aircraft. Okay, there's your LP pressure filter. There's a standard fuel pump. Now, it won't be a variable one, it will just be a standard spur gear. We're not looking at variable speeds, we just want one set of pressure, really, pretty much. Then you have your high pressure filter. Okay, you have your governor, all right, so controlled by the flyweights, all right. You have a pressure adjuster there, acceleration limiter, so we can adjust how much acceleration goes up there by restricting the flow, and a drain when it finishes. Okay, all controlled by air pressure as well. And you have a high pressure relief valve, and then eventually there's your fuel solenoid valve, which will be activated at 10% RPM. So yes, we can get fuel going to the burners, but not until it gets to 10%. And then eventually it will go off to the burner. So just a very, very basic fuel system there, all within this black line. So that's your fuel control unit, okay, FCU. So that's all inside that. Okay, as RPM increases, compressor pressure increases, hence why the air pressure will sense on that diaphragm there and control the acceleration. If high GT occurs, the thermostat opens, venting control pressure, bypass increases, fuel for combustion is then reduced. Normal ration, the governor senses APU speed. So, okay, again, that'll sense that there as well. Electronic speed switch assembly receives speed signals. The APU mounted tachogeny, your speed sensor. As the APU passes through each control, we're going to look at speeds of 35%, 95%, and 110% relay switch. We'll just look at shortly. and they'll do different parts. So fuel supplied, like I said already, from the main fuel tank through an APU fuel switch, which opens on the master switch in the on position. So again, let's go through your LP fuel pump first, low pressure filter first to pump. So as we said, at 10% RPM, the fuel solenoid valve opens and fuel is supplied to combustion chamber. So your fuel solenoid valve, so the previous diagram there. Okay. No point in supplying the fuel before that because there won't be enough air coming in. We need to get that, remember, going back to normal engine start, rotation, fuel, ignition. Well, we need rotation first. So roughly about 10%, we've got enough airflow coming into the APU to allow us to mix fuel and then put on the ignition. Again, quite fuel supplied by acceleration control bypass valve, sensors control pressure. RPM increases, compressor pressure increases, reducing the bypass fuel flow, hence more fuel is supplied to the combustion chamber. And I've mentioned already, if EGT occurs, thermostat opens, venting pressure, which then allows the spring to go up and reduces the flow to the burners. In operation, the government sends AP speed, regulates the fuel flow, and bypasses some of it to maintain constant speed. So there's no in-between speed, it's pretty much, it'll just maintain the constant speed there once the loads and that also apply. And as I said before, an electronic speed switch assembly receives speed signals from the APU mounted to the tacho generator. The tacho geni is your speed. Okay. So the 3% we're going to look at is your 35, 95, 110. And this is all within a certain relay. So it's basically 3 sets of micro switches that as the engine gets, so the APU gets to 35%, it will activate a micro switch. As it gets to 95%, it will activate another micro switch, and so on for 110. And we're going to look at what these ones do. So contacts provide control functions such as starter cutout, ignition cutout, ready to load, overspeed, and normal shutdown. So let's look at a very basic sort of start sequence for a typical APU. At 35%, that motor will rotate the APU, and at 35%, the 35% relay will operate. So it's activated, it will de-energize the starter circuit. In other words, it's going to switch off the starter circuit. We're now going fast enough at 35% that we don't need the starter anymore. The starter's done its job, it's going, the APU is going fast enough, so we don't need it. So that first micro switch switches the starter off. 95%, well, we're almost there, we're almost at 100%. So at 95%, reaches 95%, the 95% relay will operate and also de-energize or switch off the ignition circuit. At 95%, we're almost there. Do we need the ignition anymore? No, it's gone fast enough, it's gone past self-sustaining, it's now, we don't need the igniter anymore. Okay, it also activates the ready to load circuits, things like air, hydraulic, and all that good stuff. 100%, and then eventually if we get to 110%, well, that's 10% too much. Okay, so if we exceed 110%, then the overspeed switch at 110% will also energize and shut down the APU. In other words, the APU has gone too fast, so it switches it off. So what does this really look like? Well, inside here you go. It's a centrifugal speed switch. In other words, you've got a shaft along here that as it gets thrown out, it's a centrifugal speed switch. The faster it goes, the faster it will move along this way. So it's going to push this lever, illustrated to this yellow. So as you can see, there's a contact there, and a contact there, and a contact there. Appropriate for 35, 95, 110. So as this shaft moves that way, it will contact the 35% first. Then as it keeps moving along, it will then contact the 95, and then eventually it will contact the 110% if it gets that fast. Okay, definitely these two, and only if there's an overspeed on this one. Okay, I can see there's a lot of screws there, so you can adjust them because springs wear through time, so you can set them up. Again, you have your seal, your gland seal is your shaft, the flyweights. So the flyweights, as they spin out, will push the shaft, just like a normal governor. It's basically like a governor. Okay, the faster it goes with the bob weights, those little the bird's heads come down again, like I said before, push the shaft along, and then activate that switch to the side for each one in turn. 110 only if it ever gets faster than that. Okay, so that's just the last one. But definitely 35% and definitely 95%. So we're going to look at the graph now, where all this happens, and we'll take it from there. So looking at the start, you've got your battery switch. We'll switch the battery on, got electrical power. Then you have your master control switch, your APU master control switch. We'll switch that to on. What should happen then, within a few seconds, your APU fuel shut off and your air inlet door open. Now, if the air inlet door doesn't open, in the logic in the circuit, it won't start the APU. The APU door has to open to allow air in. If it doesn't, it will shut down. Aircraft I used to work on Tornado, it was the same thing. Sometimes the actuator which opens the door, the signal would go to it, but the actuator is stuck. Okay, so until the door opens and reaches another micro switch to tell the circuit, yes, the door is open, it will shut the APU down straight away. So you might hear a door try and open and then shut down. Usually things go wrong is faulty micro switches. They get dirty, oily, and that sort of thing as well. So it's one of the common things. If your APU won't start, check the door is actually working properly. Check the electrical solenoid. APU, then we've switched it on, we've got power there, the door should open. Then we've got a momentary start switch where we turn it, it's on a spring. As soon as you let go, it will stop. Just like an ignition switch on a car, you turn it, you release it, it will spring back. Same for an APU. So we hold it for maybe 1 or 2 seconds, and that will energize the circuit, provided, as I've said, that the door has actually opened. So everything going fine, okay, the starter motor will start to spin, and at 10%, you'll have your sequencing oil pressure. The LP1 closes, okay, once it's sensed to 4 psi, which is roughly 10% RPM, okay. So that basically the oil light will go out. Same time, your fuel solenoid valve opens and your ignition system is energized. We've got rotation, we've got air, and now we're going to get the fuel coming in as well. Then we move up to 35%. So remember the first micro switch, 35% switch opens. We don't need the starter motor anymore because we're going fast enough. So starter motor say, thank you very much, I've done my job, I'm finished. Again, it's also is limited by a time limiting circuit. So again, if we get past 10%, but we're slowly getting to 35% within usually about 30 seconds. If it hasn't got fast enough to 35% within a certain time, it will also switch down because there's maybe a problem with the shaft of the engine or whatever it is, or anything. It could be anything. If it's slow to rotate to get between 10% and 35% within a certain time, it will also shut down. And roughly about 37% thereabouts, your number 2 LOP2 switch will open or activate at 55 psi. In other words, it gets armed. So your low oil light pressure light will go off. Okay, that's when the light goes off. This all happens very quickly. You can imagine from 10% to 37% is all very quick. So at 55 psi, your light will go off, and if it reaches or drops to 45 psi, your light will come on and your APU will switch off. Okay, so that's roughly about 37%. And then from 37% up to 95%, it's just doing its thing. Okay, we'll go up to 95%. Your 95% switch out of the 3, your 35, your 95, 110. 95% is energized. So what does it do? APU bleed switch is armed, so in other words, we can put air bleed on. You also have hour meter. There's a little clock on the APU for how many hours that has been started, and that's part of your servicing checks, is to make a note of the hours of the APU and put it in the logbook every time you check it. Your APU gen off bus light limits, in other words, you've got electrical power. Ignition, we don't need ignition anymore because at 95% we're almost fully working. And then we also have what's called a 3-way pneumatic solenoid valve energized. We'll come on to that later. Your low oil pressure auto shutdown system is armed, and pneumatic solenoid valve arming relay is also energized. So at 95%, it does quite a lot. Okay. If all that's happy, we'll then look at 100%. Well, 100%, we're fine. We're normal running speed. And to give you a rough example, that APU is spinning roughly about over 40-odd thousand RPM, very, very fast. Okay, in this case, about 42,000 RPM. And then if there's a reason we lose control of the fuel or whatever, and it reaches 110%, it will automatically shut down the APU. Okay. And that's a basic starting setup for an APU. The main ones to remember are your LP1 switch, LP2 switch, your 35%, your 95%, and 110%. What happens at those three positions? Okay. But again, we'll recap those later on today. Right, let's look at the bleed system. So we can use the APU for electrical power, hydraulic power, and air power as well. So again, the APU is used for supplying bleed air to the airplane's pneumatic system, and the bleed air supplied through the bleed valve. So bleed valve, it's a solenoid controlled pneumatic, or could be pneumatically controlled as well. Bleed switch is simple on-off. And you have a three-way pneumatic solenoid valve as well. I'll also have a control thermostat which opens at 650 degrees C. You'll have immersion thermocouple, I'll put it 695 degrees C. Again, just more for information, don't worry too much. You'll have your standard 95% RPM speed switch, a surge bleed valve, and what's called an R38 air ground relay. That's one of the common things that goes wrong, is that R38 relays. Anything with a relay in it, these tend to break through time, and that can cause a lot of problems. A lot of diagnostics is check your relay first. So operation. When APU reaches 95%, so we're pretty much close enough to 100% speed, your three-way pneumatic solenoid valve connects the thermostat to the bleed valve, and the APU bleed switch is armed. In other words, is ready to use. Okay. If you put the bleed switch to the on position, energize the bleed valve solenoid, and the valve will open. And as the air is taken from the APU speed is restored by addition of more fuel from the speed governor. The speed governor will sense that and will speed up more fuel and make sure, because we're taking a load from the APU now, in other words, we're losing some air. So if you lose some air, like we saw on the jet engine, the bleed valve, if you bleed air away, you lose a bit of thrust. So to maintain the speed, we will now supply more fuel from the governor. If EGT increases to 650 degrees, the thermostat opens, the valve modulates towards the closed position. That reduces the load and hence also reduces the fuel. Because we're bleeding air away and we're increasing the speed or increasing more fuel, we have to watch EGT, because increasing more fuel, we're heating the engine up. So if we get to a rough about 650 degrees, well, it's just getting a bit too hot. So it will move to closed position automatically and therefore reduce the load and therefore reduce the fuel supply. And there's a typical bleed valve control. Look at the top here, you've got your standard 28 volts DC from supply, from bus bar, APU ground control unit. There's your 95% switch, so it's what energize the bleed valve setup. Okay, you've got APU bleed valve switch, open, not open, so make a switch. Okay, there's your meter fuel valve, fuel flow from the APU. So your basic APU control there, air inlet, and then your three-way selector, three-position selector. Okay. APU speed unit with the speed governor will control the fuel flow to maintain that speed. All right, and your over temp switch again will sense if it gets 650 degrees or more, which will then switch the three-way valve to close it to stop bleeding air off, which will slow, we'll put some load back on the engine and we'll slow it down. Okay, so that's just a bit. And there's a good old air R38 air ground relay. Okay, it's just a basic one. You don't have to remember too much about that one. There's your thermocouple and exhaust. So again, that's your EGT probe, and that will sense it as well. Okay, so that's just a basic setup. Okay, look, let's see where we're. Right. So a bleed valve schematic. It's just a glorified version of what the bleed valve we saw on the jet engine is. Okay, so you got your fuel control unit. You got your three-position solenoid valve. There's your solenoid valve. switcher unit, a micro switch, ambient pressure. Over 95%, it's ready to load. So at the moment, this is the actual bleed valve here. All right. The bleed airflow is ready to be allowed to go wherever for cam conditioning or pneumatic supplies. In the rate control valve, it's called the rate control, but it controls the rate of how much air comes out. So again, you'll have your thermostat, you'll have chambers A, B, C, and D. Now, depending on what's happening here, will depend on basically if it's going to open or close the bleed valve. All right. So remember, 95%, it's ready to be activated. Okay, and we can switch it off and on as required. So you can see here, we've got air supply, we've got micro switches going on, air pressure regulator. So at the moment, it's pushing up there. We have everything's in the closed position. Now it's in the open position. Okay, so now we can get airflow going through. Air bleed is selected. You can see here, I'll go back to the previous diagram. Everything's closed off. The switcher valve. Okay, there's a solenoid. So we select the solenoid. Up it goes. Solenoid activates. It opens this one. All right. So it allows the airflow to go through, to go underneath this diaphragm, pushes up there, and depending where the selector is, allows the valve to open or not, and provided we're below 650 degrees. Okay. All's good. So that's a basic air bleed valve. Controls indicators. Yeah, you have controls also in the cockpit, and you also have indicators in a ground panel unit for engineers like yourself to go and check them. And this, it's one of many. I mean, there's loads of different types. This is a ground unit. This is the sort of thing you might see in a ground panel. And this is your sort of switch you might see in the cockpit. But certainly this would be possibly one in a ground panel unit. So maintenance, oil pressure, fault, overspeed, 110, electrical power, temperature in there. Okay, and a fire control button as well. So again, we've got control of the APU. It's its own little system. Normally the APU can only be started from the cockpit, but can be shut down from either location. Operation of an APU, monitor by exhaust temperature, again recording all hours, dependent on installation, and so on and so on. Now the fire control unit, we'll just move on to the next one. With safety, danger zones, created around intakes and exhaust units should be kept clear. All right, make sure you've got the hot exhaust gas coming out, so make sure people are aware of that. Very noisy, high-pitched noise from an APU, so ear defenders should be worn. And sometimes prolonged ground operation, high ambient temperature conditions may cause a build-up of temps in APU bay compartment and also in the nearby compartments. So again, if you're in a hot environment, keep APUs running down to a minimum, but again, if you do a lot of testing, you might have to do that. Fire extinguisher should be positioned to adjacent aircraft, but make sure it's not in line with the exhaust unit. You want to be to the side of it somewhere, because if there's a fire or if something goes wrong with the APU and it starts spitting turbine blades out, you don't want to be in line of the exhaust unit, because those turbine blades will come flying towards you. So make sure you're in a safe area. If the APU is being used for pressurization test, it must be ensured that smoke masks are available by use by personnel within the aircraft, just in case there is a fire. On small aircraft I worked on, military, we don't have to worry about that. But certainly big commercial aircraft, you're inside, yeah, potential fire, you need to have that available. Make sure, like anything, APU, engine runs, any sort of work you can in aircraft with a functional test of anything, or starting engines or APUs, make sure you have a good communication link between yourselves in the cockpit and your safety person or persons on the ground. Okay. A lot of time you use hand signals, and sometimes the communications fail. You'll also have a good set of hand signals just in case something goes wrong. Okay. See how it goes. And to work an APU in situ, the power supply unit must be isolated, as I've already mentioned. A warning notice should be placed in the cockpit to indicate work has been done on the APU, so we don't allow any other people to put electrical power on. When working APU located below the rudder, personnel should keep clear of the rudder, and a notice displayed in the cockpit warning personnel not to operate rudder controls. Now, if you're working the APU, you shouldn't really be working on hydraulics and the rudder, okay, because obviously it's a big commercial aircraft, it's hydraulic controlled. Sometimes they'll put a lock on the rudder pedals, so physically you can't even move the pedals, okay. Electrical energy and APU ignition system, yeah, very lethal. Again, we mentioned this already, but also always worth a recap. So again, the power supply, the system should be switched off and at least 3 minutes allowed to elapse before handling the system. 3 minutes if it's an air gap igniter. Air intake doors must remain closed when the APU is not required, and on occasions before using de-icing fluids around the aircraft trailer. Again, if you're de-icing an aircraft, make sure if you switch an APU off, the door should de-energise. But sometimes if you disconnect electrical power, you might have had the switch of the APU on, it's left the door up, you're not starting the APU, but you might have, so just make sure the door is down. Right, APU should be allowed to operate at no load. In other words, no bleed air, no hydraulics on, and nothing else on, just normal governing speed for roughly 2 minutes before shutting down. You might have had a load on the APU with testing hydraulics, whatever, basically like a normal engine, switch everything off, allow the APU to settle down for at least 2 minutes, lets it get back to establish its normal cooling, its fuel flow, RPM, and then once it's happy, then you shut down as normal. After shutdown, sufficient time should also be allowed for the APU to cool down before carrying out maintenance on the unit. Yeah, you don't want to burn yourself. You're going to, you maybe find a leak as the APU is running. Yeah, APU, small jet engine, but very high temperatures in there. So if you've got a cowling, it's accessible cowling to see it, you need to work on it, open the cowling door, yeah, go and get your tools, go come back in about 10, 15 minutes, let the APU cool down sufficiently enough. No point in burning yourself. So a few checks before starting. Ensure there is sufficient fuel in the aircraft. It's always embarrassing, you go to start an aircraft engine or an APU and you've not refueled the aircraft, okay? So make sure you've got plenty of fuel. Likewise, make sure there's plenty of oil and replenish if required in accordance with the maintenance manual. Before we start it, make sure there are no leaks, fuel leaks or oil leaks. Check the drains, check your dry drains, check your wet drains. Is there anything leaking out? Have a quick check. Make sure there's no obvious signs of leakage. So again, check out the drains and to ensure they are open. Any covers and blanks? Yeah, there might be blanks depending on the aircraft type. Make some sort of blank for the exhaust of the APU and anything like that as well. So make sure any blanks that are covered are removed. Make sure electrical power is available and check that the fuses, circuit breakers for all the systems for APU operation are intact, reset and closed ready to go. Again, you will follow a pre-start sequence of events in a book operation. Again, once you come compatible, you'll probably know them off by heart, but always make sure they've not been updated or modified. So with direct power on, check indicator lights are illuminated as appropriate of the APU installation. So you do your power on checks before you actually start the APU. Checks made on indicating devices associated with automatic shutdown circuits to ensure they are clear of relevant ones. So you do a lamp test to make sure any warnings will illuminate should they come on, and you do another few checks as well. Make a note and record outside air temperature and the hours run by the APU. Okay, so again, there'll be a little clock in the APU, and you make a note of those as you, because after so long, the APU will be removed for normal servicing, just like a standard jet engine. Then what you'll do, you'll check the fire detection system for serviceability. In other words, you press your fire test button on the panel, again, illumination come up, you might even warble, and that just proves your continuity of the system. Now, important thing to remember is it also shuts down the APU. So before you start an APU, you're checking it, and that's fine. But be aware, if you've got a fault and you've got a fire and it hasn't gone out, you can select fire test button, and it will also switch the APU down. I can prove this because we were rushing about one day, went out to do an APU run very quickly, jumped in the cockpit, got it all sorted out. In my head, I forgot to do the fire test button. So I pressed the fire test button, forgetting the APU was already on. So I pressed the fire test button, lights come on, boom, APU shut down. It does work, okay? So I've only done that once. So make sure you test it before you run the APU. But at least it proved the system did work. Okay. There's an example of an APU control. There's your master switch. So off, on, and start. So remember, From off to on, it's just a click, but from on to start, it's like ignition in your car. You can switch it to start. As you release it, it will switch. It will move back to the on position. Okay. You've got APU generator buttons. Any faults will come up. You've got your secondary power systems, basic fuel controls, cross flow, drives. You've got twin engines. You might have power drive or PTO drive, backup generators. I mean, that's just a typical example. We've got different ones for different aircraft. Okay. If you have, just I want to remember as well, if you have shut the APU down by mistake and using the fire test button, make sure you switch your selector to off as well, because the potential, if there's a fault or something like that, it might try and start itself again. So make sure you always switch it to off. It can be because it might have automatic shut down, maybe because of an overtemp or an overspeed, so it's automatically shut down. So if you get any of those systems, please make sure you do switch the switch to off before you go and check the APU. Okay. All right. Anything else? I'll go through there. That's okay. Good. Cautions. If light up does not occur or the APU does not reach governed speed within a specified time, again, like I've said there, the master switch should be selected to off. So again, LP2, it might sense that. If it doesn't reach the LP2, 55 PSI, within a certain time, it will automatically switch it off. So I've said there, something's gone wrong, make sure you switch this off. Before attempt to restart, sufficient time should be allowed for the excess fuel to drain overboard and allows the APU to cool down. We were learned to do, for example, no more than 3 starts within a 2 minutes cycle. So we could start an APU, we could shut it down, we could wait a minimum of 1 minute, start it up again, and then we could shut it down. If it didn't start within 3 minutes, we had to wait a good sort of 5-10 minutes before we go for another start, because not only trying to potentially heat the APU up, the starter motor is getting hotter and hotter and hotter. Every time you use the starter motor, it's getting hotter and hotter. So again, follow your precautions for the maintenance manual. So number of successive starts should not exceed, again, as it says in the maintenance manual, and care should be taken to ensure the batteries and starter motor are not overheated. Yeah, you're taking a load from the battery's going to get hot as well as the starter motor. So again, don't start, shut down, start, shut down, start, shut down, start. You're going to put a lot of stress on the starter and the battery. Now, it might be an internal start from the aircraft battery, or it might be using external power. Always try and use external power for any ground maintenance to preserve the aircraft battery where possible. Should the APU not start after the specified number of attempts, again, the fault should be investigated and rectified. Again, make sure you switch your switch back to off before. It could be something simple as not enough fuel. APU door has stuck, so there's no air being to come in. So if the door doesn't open, it certainly won't do it. LP1 switch, LP2 switch, the centrifugal contacts, the 35 and 95, whatever. Could be a lot of things, but you will follow the maintenance procedure. You will learn common faults as you get more experience. But again, don't just start ripping the APU out saying, oh, it won't start, it's broken. It can be something very simple. An example of that is, again, one tornado aircraft worked on. My other shift, I was on night shift, they were on day shift. They had an APU, would not start. They couldn't get to start at all, so they got the specialist test equipment. We called it a disco box. It's got lots of lights and gauges. So they were setting up to go and test the APU, and they were getting to the point of possibly removing the APU. So they did the handover at shift change to myself. I sent one of my juniors out, a highly experienced guy. I said, tell you what, just start from start and see what you find, just before we start ripping things apart. So he went out and he came back within about 2 minutes. He fixed it. What it was, some aircraft have this, some aircraft don't. On our aircraft, we had a ground switch in the undercarriage bay, which technically should be switched to off as you're doing your servicing around the aircraft as a safety. So when you open the APU door, there's no chance of APU coming on. So this guy had done his job 100%. Normally we wouldn't bother with it, we'd just leave it as it was. So all it was the safety switch had been activated, and the previous shift checked that, because normally it wouldn't be switched off. But there was a new person who had come out of training, and he was following the book 110%, which is fair play, exactly what should have been done. So just some common things. So it was a very quick fix. So my junior came back in, big smiley face, fixed. So again, think simple first. Don't start diving into, oh, the engine's not spinning, replace it. Think simple. It could be something simple like a circuit breaker, a micro switch. Okay, follow the book. Make sure you don't just jump ahead of the game. Okay, that can save a bit of embarrassment as well. When an APU is operated at governed speed, the exhaust gas temperature is constantly checked to ensure limitations are also not exactly the same as you do for a normal gas turbine engine. You're constantly monitoring. Even in your cockpit and the APU started, that's not you finished. You're keeping an eye on for any faults, over temps, fuel flow, etc., and RPM. Any limitations be exceeded, the electrical and or bleed air load should be removed as soon as possible, and AP shut down and cause investigate and also rectify. Again, following your maintenance manual. So always look after your APU. Make sure, as you do like a normal engine run, that you're following, keeping an eye on everything that's going. Any detection, again, make sure you carry out everything appropriately. You won't be allowed to do an APU unless you're authorised. APU shutdown, well, when's going to shut down? 110% overspeed. High EGT and above 650. Loss of EGT signal to the electronic system. Yeah, if it's lost the signal, then it doesn't know what the temperature is. So as a precaution, it will also automatically shut down. Okay. Oil pressure. Well, low oil pressure, that'll be LP2 switch. It's gone below 45 psi. Or likewise, it's not reached 4 psi on your LP1. It won't allow it to go any further. It all depends on the APU type, but very, very similar. High oil temperature as well. Yeah, if you get high oil temperature, well, there's no point in keeping the engine running, or the APU running, I should say. We're going to cook the oil, 124 degrees, it's going to oxidize. Okay. As mentioned before, you can also shut down the APU with the fire test button. Okay. APU fire detection system operation, automatically or manually if you use the test button. Opening or closing of cooling air shutoff valve before 95% of over the governed speed has been reached. That will also put too much load on the APU, and that will automatically shut down as well. So make sure you allow the APU, don't go too quick, don't go chucking the cockpit. It's almost 95, well, that'll do. No, let it go through its system. Once you're happy, let it settle down, then you can activate the air load. Overheating the APU bleed air duct just forward of the APU environment compartment, yeah. So any hot air, over temp sensor again, too hot air coming in, well, that can potentially starve the APU of enough oxygen. So again, overheat, we will shut down as well. When specific or specified airspeed and altitude limitations are exceeded, some aircraft APU is normally kept running until takeoff, where when the weight on wheel switch disengages, it automatically shuts APU down. So some aircraft, they tend to keep the APU running just in case for takeoff, that in the event of an engine failure or engine failures, they have electrical and a little bit of hydraulic power to possibly recover the aircraft if possible. But when the weight and wheel switch disengages, that will automatically shut the APU down as well. So this goes into that one. Operation landing gear switches on takeoff. APU normally shut down by allowing it to operate for, again, as I said already, no load on the APU at all for approximately 2 minutes. Let it cool down, let it stabilise, and then let the engine APU shut down. Okay. Right, that's about that one in there. So we're checking there. Any questions on APU? Again, we will recap it. How are we doing for time? Not too bad. In fact, yeah, let's go for another quick break, 20 minutes, and that's a good point to start. We'll come back. We'll do a bit of recap on APUs before we start on the power plant installation. Okay, basically engine installation. Okay, so let's go for another switch. Energizes, allows operation of the the APU bleed valve. However, remember, another way of shutting the APU down, if you switch that switch on before it gets to 95%, that puts too much load, it will also shut down the APU. So there's another one just to remember. Okay, what should you also do? If you're running an APU, what should you also record? Or take a note.
Temperature.
Temperature, yeah. So your oil temperature, yeah, fuel, anything else. And what about it's actually on the APU? You might want to take a note of a certain number. So you can write it in the logbook.
Hour?
Yeah, 80 hours. Yeah, you might make a note of the hours. You certainly, it depends on the commercial aircraft side, but on the military side, where we did it, we would take a note of the hours once the aircraft had landed. We do an after-flight servicing, and we do the oils and all that good stuff. And we'd open the APU, check APU, and we check the clock, make a note of the hours, write that down in the APU sheet. Okay, good. Excuse me. At what temperature does the control thermostat open up? The control thermostat. That's when it opens and reduces the fuel flow because it's getting a bit hot. Doesn't shut it down, but it's getting a bit hot.
650.
650, yeah, good. And which one will show you there? That's fine. That's fine. What's the number of the air ground relay? R what?
38.
R58. Good. Okay. This is the one you want to remember because there's usually a question or two on whichever one of these three. What happens in the APU starting sequence? What happens at 35% RPM?
Switch off the starter circuit.
Good, yeah, because 35%, it's going fast enough now. We don't need a starter. Good. 95%?
No ignition required, so the ignition is switch off.
Yeah, no ignition one. There's a lot more goes on with 95, but that's the basic one you want to remember, yeah. And 110%?
Yeah, if it exceed the 110% RPM, it will switch off. APU will switch off.
Good. That's the three basics. Yeah, but 95%, you've got a bit more. You've got your hour starts, your generator light, buzz light and all that's a good thing, ignition off, three-way pneumatic valve and that sort of thing. But if you remember the three basic ones for 35, 95, 110, you're pretty much halfway there, okay? At approximately 10% RPM, what valve opens? What valve opens at roughly about 10% RPM?
Oil pressure, LP1, low pressure 1.
Yeah, that will. If it senses 4 psi, it will allow the ignition and the fuel. But yeah, it's a fuel solenoid valve open at 10%. Yeah. Good. Where do we get fuel for the APU? Is it?
Yeah, from the tank, main tank.
Yeah. One of the aircraft tanks. It doesn't have its separate tank. It's just one of the aircraft. They'll be allocated to the APU. Good. The oil temperature switch is set at what temperature range to close the APU down? So what the oil temperature switch will activate at what temperature?
124 degrees Celsius.
Yeah. 124. Yeah, it's too hot. We're cooking oil. Okay, unless we make it a nice curry, we don't want it that hot.
If the temperature exceeds above 124 degrees Celsius, it will shut down.
It does, yeah. Thank you very much. Good. Okay, LP1, LP2. Remember, LP1, 4 psi, LP2, 55, and then we'll shut down at 45. So lower pressure switch 1, which is number 1, lower pressure switch 2, number 2. Remember those, all is good. The pressure relief valve opens at what psi?
90 psi.
90 psi, yeah, good. Oh, winner, chicken dinner. Fantastic. Yeah, that one's all right. Okay. What type of oil system is fitted to an APU? Is it a dry sump or a wet sump?
Dry sump?
Yeah, dry sump. It's got an external oil tank. Yeah, external oil tank. Good. Again, it's a fully recirculatory oil system. We don't mention it there in the book, but as you can imagine, it's just fully recirculatory, nice and straightforward. Okay. Good. That one's all right. That's fine. Okay, let's go back away. So we had. Oh yeah. Talking about if you get a free turbine overspeed, okay, what was the approximate percentage that the engine will be shut down automatically if a free turbine, say, shaft breaks? When would the engine shut down? At what percentage?
If it reaches 120.
Yeah, 120. So it shuts the engine down. What also does it do?
It will prevent the fuel flow.
Yeah, prevent the fuel flow. Will shut the engine down. But on a twin-engine aircraft, twin-engine helicopter, what else will it do? So we'll shut the bad engine down, the broken engine. But what else?
And then it will like inhibit the restarting.
Yeah, you can inhibit the broken engine. What about the good engine? Will it do anything to the good engine?
Good engine will be on run.
Yeah. What does it prevent the good engine from happening? Or happening to the good engine? So it shuts down the one with the broken shaft, but what does it also prevent on the good one? Anybody? No. Okay, also it will shut down the engine with the broken shaft. It will also inhibit the good engine from automatically shutting down as well, because that's the only engine he's got. So to prevent automatic shutdown, it will also cancel the automatic shutdown circuit. And so inhibit the good engine from automatically shutting down. If he loses the shaft in that one, well, that's it. There's not much joy. He's coming down, you know. Okay, in order to restart it, you'd have to reset the resetting point back to default position. But again, are you going to do that with a broken engine? Probably not. What does NF stand for? The abbreviation NF.
Free turbine.
Free turbine, good. Or power turbine, good. What are the two main controls in a helicopter? The levers. What are the two levers called?
Cyclic.
Yeah.
Collective.
And collective pitch.
Good. Cyclic and collective. Which one only moves one pitch of one blade at a time?
Is cyclic?
Yeah, it's cyclic, yeah. So that's cyclic ones, your forward, your back, your left, your right. Yeah, so just think of it as cyclic. The collective does all the rotor blades. It will change the angle of attack of all the rotor blades at the same time. So increasing height, decreasing. Now, what do we call the name for when the blades change the angle of attack but decrease the RPM of the engine? What was the name we gave to that?
Static drop.
Static drop, yeah. So basically the shape of the rotor bends up the way, which is great because it's getting lift, but because it's putting more load on the engine, like we saw in module 17, it slows the engine down. And it's also decreased the distance from the rotor blade tips. So you've decreased the disc area, that amount of lift that we can potentially get from it. So if it decreases lift, It decreases RPM. Well, the helicopter's going down the way. Yeah, we're sort of stuck there. Okay, static droop. Good. So how do we recover static droop? What happens there? How do we recover static droop? So we want to go up.
Yeah, we have to increase the fuel flow rate.
Yeah, so what's the name of the system that does that? What do we call that system that's on the collective? When the collective gets moved, in the old days, it was a pilot because he would twist the throttle on the actual collective, but on the new ones don't have that. It's just a lever, it pulls up.
Anticipator.
Anticipator, yeah. It does what it says. It anticipates the movement of the pilot on the collective lever. So as he's going up, it says, right, we need to go faster. He's wanting to go up. So depending on the speed of the free turbine, it will allocate more fuel to the fuel control unit, which will provide more fuel to the burners, increase RPM, which will increase centrifugal power to the blades, which the blades will come from being in a sort of C shape, come flat again. That'll maintain the disc area and maintain the lift and preventing static droop. Yeah, good. The ratio, what's the typical epicyclic gear ratio formula? Typical one.
Driven gear over driven gear plus fixed gear.
Yeah, I mean, it can be roundabout. For the purpose of examinations, though, just the 1 inch in your book for the moment, that is fine. Okay, they won't give you that one and then the flip version because that means the same thing. Okay, you'll just get an inverse number. What's bigger, your crankshaft or the drive shaft gear? So what would be bigger, the crankshaft gear or the drive shaft gear?
Drive shaft?
Yeah, drive shaft's always bigger. Depending on the reduction gearbox you've got, depending on the system, a standard spur gear would be a small crankshaft gear. So basically the crankshaft is going that fast that if it was the same 1-for-1 ratio, the rotor would be going too fast. So we need to do reduction gearboxing, and I'll just highlight myself. What would be the typical reduction ratio for a main rotor and a tail rotor ratio?
Around 5:1.
5:1 for a tail, yeah, and for a main rotor?
And for 100:1?
Yeah, 100:1, yeah. So you could have an engine actually spinning round about 20 to 30,000 RPM. Do you want your rotor blades spinning at 20,000 RPM? No. So we can reduce it down to about maybe 250 RPMs to maybe 530 RPMs, okay? The rotors tend to spin the same speed apart from when the collective is getting used, okay? But they'll pretty much stay the same speed for forward, back, left and right. Again, depending on the type of helicopter, the size of the rotors and the ratio. All right, what's the purpose of a freewheel unit?
To rotate the blade, helicopter blade or propeller.
Yeah, and yeah, the rotor as well, good. So that's fine with that one. Good. Always good that way. Right, going back away to turbo shafts. Turbo shaft engines are subdivided into two groups, which are just the same as turboprops.
Yeah, free and power and fixed turbine.
Yeah, direct drive, free turbine or power turbines, good. Okay, and again, you might get the shaft coming at the back of towards the exhaust. Again, main thing, free turbine. Oh yes, forgot to mention, is with the free turbine one, especially in helicopters and turbo shaft engines, we can start the engine up to do some power checks and that sort of thing, but we don't want the rotor spinning, okay? So we can put a rotor brake on there and we'll have some sort of a brake rather than a clutch. So we actually, like a brake on a car, we can put a rotor brake on there, and that, like the turboprop one, we can stop the rotor from spinning, but we can have the engine running for hydraulics, electrical, air, whatever, okay? So just make a note of that one. All right, then go further back again. What's the purpose of an anti-vibration coupling?
Compensate vibration.
Yeah,
Create
they're very, very thin washers. Squashed again, because they're thin washers, they're not solid. It absorbs any sort of vibration or helps prevent any vibration from a flange on a shaft to another component. Okay, good. And again, what was the three methods of joining shafts together? Or couplings, or three types of couplings, I should say.
Yeah, curvic, gimbal, spline.
And spline, good. What was the purpose of the flexible diaphragms in the gimbal one? So in the gimbal, it looks like a little dumbbell. There's little flexible couplings. You can squeeze the couplings. What was the purpose of those?
It allows to connect shaft.
Yeah, it just allows a little bit of misalignment,
Yeah.
because, you know, just by heat expansion, so we can just, rather than solid, and then being out by maybe 1 millimeter or 2 millimeters, be a little bit misalignment, we could put it in there. Good. Okay, so that's the three of those. Oh, happy chappies. Right, let's go back a little bit from last week. We'll recap a little bit of last week's. LP shaft disconnect system. What was the basic function of an LP disconnect system? Mechanical one. What basically happens with the mechanical?
Notable. Prevent the turbine from catastrophic self-destruction.
Yeah. So what happens? What moves to move something to switch your high pressure shutoff valve?
Bill crank.
Yeah, you've got basically a nut and a bolt. Yeah, your nut is fixed to the turbine disc, and the bolt is on the shaft. So if one of those breaks, the shaft breaks, the turbine disc will still spin, but the shaft won't. So basically, the bolt will unspin. How many turns?
3/4 turn.
3/4 of a turn, yeah. Not even a full turn, only about 3/4 of a turn. That will spin, will go back away. That will then move the little lever, yeah? And what was the lever attached to? So the nut moved the lever, then the lever did something. You remember? What did the lever move?
Move the.
It was a cable, yeah, it was attached to a big cable, and the cable went all the way through the engine, came to the front, then came to the lever that was on the attachment of the high pressure shutoff lever, so it would snap or come off its recess, and that would close your high pressure shutoff valve. Okay, just by purely nut and bolt action, the bolt would spin if it seized, because the turbine would keep moving. Move the little bell crank. The bell crank was a mechanical lever, so the nut would move the lever. Lever would be attached to a cable all the way to the front of the engine and switch over. That was a mechanical version. On the if you had an electrical version, input to the FAFC, there'd be a phonic wheel. So again, the change in the distance between the sensors, it would immediately produce a faster signal. The FAFC would recognise that, and then it would operate. Do you remember what it was called? What was the component the FAFC would operate to shut down the engine? It was 1, 2, 3, 4, 5, 6 letters.
Pressure raising shutoff and dump valve.
Yeah, the PRSODV. Pressure raising, shutoff, and dump valve. Good. Okay. Mechanical speed governor, overspeed governor, typical one. Operated on a principle of a valve moving up and down to close or increase the servo flow. the bob weights. So you have like the looks like bird beaks coming down. Centrifugal force, that was fine. Okay, that was okay. That one. What do we call the range when the power lever is brought back through a mechanical stop at idle and goes back the way? What do we call that range? Where it goes from flight fine to ground fine and then into, what was the name of the range? The power lever, you're at maximum, you're at idle, and then you're at flight fine, ground fine, and you put it through a gate. That is now in, what was the name of the range called?
It's beta range.
Yeah, beta range. So we're in thrust reverse, yeah? Thrust reverse range, good. Okay. The propeller control lever is usually connected to which lever?
FCU?
The propeller control unit, sorry, yeah. Propeller control
ECU.
unit. Yeah. The power lever, if you use it in thrust reverse in the beta range, what was the angle we could move the blades to?
Plus 20, minus 20.
Yeah, plus 20 and minus 20.
Positive.
Positive 20, minus 20. Dual lever controls, so your power lever and your condition lever or your prop control lever are normally used on what type of engine? Fixed
Power.
turbine engine?
Power.
Yeah, or free, yeah, good. So yeah, so a single lever is usually a fixed turbine for easier control. All right. Okay. Covered that one. Again, going back away for last week, last Friday, what was the purpose of the LP cock?
For the maintenance purpose.
Say again?
For the maintenance purpose.
Maintenance, yeah, maintenance purpose, that was one of them. What
And
else could you use for?
emergency situation.
Good, yeah, emergency.
Isolate.
Good. Emergency and maintenance. Again, LP cock is just a simple ball valve, 90 degrees operation, either through a lever or solenoid motor. Again, so it's solid on one side, got a hole in the middle. Again, make sure you use that for maintenance. Saves you defueling the aircraft, and also for emergencies. The HPSOV or HP cock usually just on off, but it might have three positions. What were the three positions?
Is fuel cutoff, position and run.
Yeah, start position and run. Good. Annual favourite. What's the 4 requirements for a control system?
Accurate in operation, positive in selection,
Yeah,
reliable under all condition of fleets,
yeah.
and effective regardless the distance between flight deck and engine.
Fantastic. Good, good, good. And remember, weather conditions, climatic conditions, like a hot country, a cold country, they will expand, contract. So again, it's crucial, especially with old aircraft, you've got lots and lots of long cables, that you tension them, you do the rigging as per the book. We don't make it too tight, we don't make it too slack, because the bigger the aircraft, the bigger the distance, so it's got to be effective regardless of the distance. Good. And turboprop engines are also split into 2 categories, which are same as a turbo shaft.
Is power and
Fix and power.
fix and power turbines.
Yeah, good. And what did we call, or what was the abbreviation ESHP stand for?
Equivalent
Yeah,
horsepower.
shaft horsepower, which was, which 2 added together?
Shaft horsepower plus jet thrust.
Yeah, good. Spot on. Okay, doke, that was that part. All right, let's see. Is it worth going back a little bit more, just for a bit of a fun? Keep you on your toes. Let's just pick some questions at random. Just to, we'll go back a little bit as well. Back in bit 2, just to keep you on your toes. What is meant by the term thermal shock?
Due to the heat on the turbine blade,
Yeah, it could be anywhere. Thermal shock can happen anywhere.
Anywhere, any material due to the large amount of heat.
Yeah, large amount of heat. Maybe something very cold touching something very hot. In our case, we use the bleed air from the HP compressor. And which we use the bleed air, which annotation would it be? Is it P1, P2, or P3?
E2.
Not quite. Close.
P1.
Then
Oh, P1, that'd be really cold.
Not
Well, definitely thermal shock.
P3.
P3, yeah, because they're already roughly about 500, 600 degrees. Good. Yeah, P1, it would cool it down a bit too quick.
And it will cause that thermoshock.
Yeah, that's it. Okay. That's fine there. Just random questions from book 2. What is the purpose of a fuzz burner?
Question, sir. Question.
What's the purpose of a fuzz burner? Or what is it? Is it, I'll give you a clue, is it to do with fuel or to do with oil? In other words, is it in the fuel system or is it in the oil system? That gives you a clue. A fuzz burner. Tends to be used a lot on helicopters, although I think they are using some on aircraft now, but mostly on helicopters at the moment, as far as I believe. So what do you think? Is it fuel system or oil system? And if so, which or what does it do? What's the purpose of it?
Forgot.
It's all right. It's been a long week. Right, it's in the oil system, if that gives you a clue. A fuzz burner. It's a fancier version of another of the same sort of component already in the, I'll give you another clue, in the scavenge line. So you'll have this component in the scavenge line, and a fuzz burner is an electrical version of this component in the scavenge line. Anybody? What do you, let's think, what do you have in the scavenge line of an oil system?
We have
Electric charge.
No, an electric charge. It is to do with electric though. Let's think what's in let's think what's in the scavenge return line. What do we have in it?
a scavenger filter.
We have a filter, yeah. We have a filter, yeah.
And
It's not
then
that though.
pump, scavenge pump,
We have a scavenge
and-
pump.
MCD,
There we go. MCD. What's an MCD?
magnetic chip detector, which will
Good.
detect the small particles.
Yep, that's right. So a fuzz burner is an electrical version of an MCD. It's still an MCD, but it's an electrical one because it allows us to do what? It's pretty much the same as a standard MCD, but it's electrical. Why is it electrical? The clue's in the name, fuzz.
To give the electrical signal to the cockpit.
It can do. The ones in the helicopters can't. This is on the debris system version. Will build up and give a circuit, but a fuzz burner will give an indication to the cockpit. Yeah, the pilot can then press a button, which will give a charge to that, which will literally burn, hence fuzz, burn the debris away. If it's small debris, the light should go out. If the light comes back again, that means there's a lot of debris. But if it's just a little bit of swarf, a little bit of build debris, you can burn it away basically, and it should go out. But make a note of that, because when he lands, you say, I had to press the fuzz burner however many times. If it comes on again very quickly, he's probably got a lot of debris. There's maybe a problem with the gearbox. So it allows it to burn away some debris and make a note of what's happened. Okay, so it's just an electrical version where you heat the debris on the plug, burn it off, and then depending how quick it comes back on again, will determine what the pilot has to do. All right, but it's just a fancier version of a standard MCD. Good. Okay, if we had an LP cooling overheat warning light come on, what might that give an indication of? So if an LP cooling overheat light comes on the cockpit, what might have, there's loads of options, but what could have possibly happened? The LP cooling light. What is that telling us? So if it's LP cooling light, that's in the cooling outlet. So a little thermocouple there, but we're getting a light come on. So why would that light come on?
Oil temperature should be high.
Not oil temperature. Remember, it's in the air duct. So if it's the cooling air has now reached above its normal temperature. So what's caused it to go above normal temperature? Again, it could be quite a lot of things. Don't be wrong. It could be quite a lot of things, but generally, though, what's happened? If it's gotten hotter, where's that hot air come from? Just think simple. Easier said than done, I know. It's come from the hot side, isn't it? We've potentially, say, a twin spool engine. We've got LP air, we've got HP air. Well, the only reason LP air can get really hot is because it's been heated up. Now, normally, if everything's working fine, it stays where it is. If it's gotten hotter, something has escaped from the HP side. We've got hot air escaping from the high pressure side. Yeah? So maybe a turbine casing, cracking something, hot air pipe within the HP side is now letting hot air escape to where it shouldn't be going. So we've got a problem somewhere. Yeah. So don't think too deep. Just think we've got hot air from the HP side. Okay. How many power supplies does the FADEC have? So again, just random questions. Just throwing it in the mix here for you. How many power supplies does the FADEC have?
Two.
Two. Yeah. Which are?
They are PMA and battery 28 volt.
Yeah. Permanent magnet alternator and your standard 20 volts DC. When does the permanent magnet alternator kick in? Or when does it activate? What
During
RPM?
startup.
What percentage of RPM?
If 50%.
Yeah, good. Yeah, 50%. Yeah, good. 50% RPM. So not quite self-sustaining, but it's fast enough to switch over because the alternator is going faster on the gearbox. Yeah, good. Okay. What is the freezing point of Jet A1?
Negative 45.
Yeah, 45, 40, 46, 47, something like that. Yeah. Okay. And let's see, that's another one. Let's see who remembers this one. No, don't explain it. Tell me the positions of the kinetic knife valve and what's happening to servo pressure.
If it is like if it is down,
yeah, so it's in, yeah.
Yeah, and then it is bleeding in the sense, yeah.
Yeah, if you've got a knife in, you're cutting. Yeah, if you've got a knife in,
it's
cutting.
bleeding.
Yeah.
In interstage, like it is constant. The flow is constant.
Good. So
And
if it's not, yeah.
Up, it is the valve is closed.
Yeah. So if the valve is closed, what's happening to servo pressure?
Pump pressure increase.
Yeah, good. Servo pressure is increasing. So servo pressure increasing, what's happened to pump output?
Pump pressure also increasing.
That's it, nice and easy. Yeah, whatever servo pressure is doing, the pump is also doing. Yeah, it's like for like. So you're quite right. If the kinetic knife valve is in, so the knife is in, it's cutting. If you've got a cut with a knife, it's bleeding. So if it's bleeding, that means servo pressure is decreasing. So therefore, pump output is decreasing. If the knife is out, pressure is building up. So servo pressure increase, pump output increase. If it's halfway in, it's stabilized. It's not increasing, decreasing, it's just stable. Good. Every time there. All right. One more for the look. Oh yeah. What are reference controls? What are stagger checks? Reference controls.
The positioning the throttle.
Yeah.
Positioning
So
of
yes.
inlining or inlining the throttle.
Good. So how would we adjust the lever? If we set the range, how would we adjust the lever to line up with the other throttle levers?
By masking tape or
Just wrap it in masking tape. No, I know what you mean. Yeah. What was the part we would change, adjust? That's what I was looking for. On the control linkage, what part would we adjust? What was the name? Would it be the radius or the length? Go on.
Radius.
No. Not the radius, the other one.
then
Length.
it will be length.
Yeah, that's it. Be confident, don't worry. Yeah. If I, excuse me, if the throttle has no movement at all, like I need to move it from A to B, I need to change the radius, okay? That changes the range, how much that throttle moves there and there. The length changes where that starts and where that whole range stops, okay? So length is where it stops and starts. The radius changes the range, how much that moves back and forward, yeah? So just watch out for those ones. Okay, that's just about a few random questions from book 2, just to keep you on your toes. And I'll probably go back to book 1 as well. Okay, what time on there? Right, that's a good point. I think let's go for some food. Come back in about an hour's time. We'll continue with the